Hi, Rosie. I feel like I can do a bit of a better job of explaining nuclear power. I'll try not to go on for too long, but really, for completeness, we've got to start kind of at the beginning and go through everything. So, firstly, the most important thing to understand, really, when we're talking about energy, is that all of the energy, absolutely all of the energy in the entire universe already exists. All of the energy in the universe came out of the Big Bang, like 13.7 billion years ago, in this big explosion. And ever since then, the last 13.7 billion years, that energy has been dissipating into space, and that will continue to happen until everything is eventually cold in some absurdly long distant future. And everything that happens in the meantime is just a process which is facilitating that heat loss into the universe. And so the sun has ultimately come for the energy to make the sun came out of the Big Bang, and we'll talk about that in a bit. And then you then get the sun's energy falls onto the Earth, radiates down to the Earth. That heats the surface of the planet, which then, by convection, starts winds moving in a very chaotic process. So now you've got wind blowing around the planet, and you can then stick a wind turbine in it and harness that and turn it into electricity. But at every step, every time you convert energy, although you can't create energy because it already exists, but every time you change its form and change it from solar energy, which is radiation, into kinetic energy, which is the movement of the wind, into electrical energy, and then you use that and turn it into heat, whatever, or motion, whatever you're doing with your electricity. Every time you change your state, your form of your energy, you lose some, and you lose it as heat. You lose it as a bunch of things, but ultimately it becomes heat. Even if you lose it as sound, that sound ultimately becomes heat because it's moving air molecules around, warming them up, and then that heat will then dissipate. So absolutely everything you ever do, absolutely everything that ever happens in the entire universe ends up as heat. And that's an important concept to get your head around. You lose at every single step, and minimising those losses is where efficiency comes in. So trying to make a machine more efficient, you're trying to lose less heat, or trying to lose less noise or less vibration, which is ultimately heat. And you always lose, and it's impossible to convert energy perfectly in any possible sense. So to understand nuclear power, we're going to start by thinking about those four fundamental forces of nature. And so we had gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. There's also the possibility of a fifth fundamental force of nature, which is in the realms of theoretical physics at the moment, where they're trying to work out what's going on with the universe on a very, very big scale. There's kind of one missing. But at the moment we know about, for sure, four fundamental forces of nature. And we're going to have a quick whiz through those now. So gravity is at large distances, gravity is pretty much the only force that is at play. When you're talking about the distances between stars, distances between planets, gravity is the only thing that's doing anything, because it works at an infinite distance. And gravity gets less and less and less strong the further away things get. But basically the way gravity works is every single atom in the entire universe is attracting every other atom in the entire universe. But the closer those atoms get together, the stronger that pull is. The more of a clump of atoms you have, the bigger an object is, the stronger its gravitational pull is going to be on a smaller thing. But that smaller thing pulls back, albeit with a smaller force. So, for example, the Earth is pulling you down onto it, but you're actually pulling up on the Earth a little bit, but it's so negligible that you wouldn't ever notice. the Earth is pulling on the moon, but the moon is pulling back on the Earth, which is why the tides happen, because the moon is pulling all the water on the planet towards it a little bit, and as it goes round, that tidal bulge moves around, and so you experience the tides going up and down. So every atom in the whole universe is pulling on every other atom. But the greater the distance gets, the strength of gravity drops off very significantly. So it's very strong. It's gravity is a relatively strong force at a very short distance, but at a long distance it becomes very, very, very weak. So the gravitational pull of the sun on an asteroid at the very, very outer reaches of the solar system is ever so small. It's almost unmeasurably small. But there's absolutely nothing else at play. In the vacuum of space, gravity being the absolutely only thing that's doing anything, it's enough to keep hold of that asteroid. It's enough to keep hold of, for the centre of the galaxy, to keep hold of the sun, even though it's stupidly far away. There is absolutely nothing else at play, and so so gravity binds the galaxy together. And as you get down to a very small radius, as your distance between your atoms and whatnot get very, very close, when you're squishing things together, gravity can actually pull things together so hard that they end up getting hotter and hotter and hotter. And so, if we think about the early universe, when the Big Bang very first happened, you got this very large explosion of all the matter in the universe suddenly somehow bursts into existence, and nobody understands why, but it did. Briefly after the Big Bang, I don't know how long, let's say a week, but doesn't matter, a short period after the Big Bang, there's nothing in the universe other than a load of hydrogen, a tiny little bit of helium, and that's it, in this huge explosion of gas. Remember, your hydrogen atoms are just one proton and one electron. So they're very, very simple, very, very light, very, very dense at this point, and expanding at an absurd rate. So we've got this cloud of almost entirely hydrogen. You might as well think of it as it did have a little bit of helium in it, I reckon, but it's effectively just a big cloud of hydrogen. There are no stars, and so there is no light, and so it is dark. It's a big, dark cloud that's expanding at a gazillion miles an hour. Over time, those hydrogen atoms start to attract, well, they're always attracting each other, but they start to clump together under gravity, and you get these vast clouds of hydrogen start to coalesce. And given time, those huge clouds of hydrogen will collect into what ultimately becomes a star. So it's a huge cloud, ridiculously large cloud of gas, which starts to coalesce, and then within that cloud you get smaller pockets of where it happens a bit denser, and each of those dense little pockets of gas compresses under gravity, and as it compresses under gravity, it starts to warm up, because the more you squeeze things, the hotter they get. And eventually it gets hot enough in that core of that, what will become a star, for those hydrogen atoms to get squeezed so close to each other that you're pushing the atomic nucleuses close enough together, even though they're trying to repel each other because of their electrostatic repulsion, squeezing them together until those atomic nuclei bond together and fuse together, and that releases a huge amount of energy, and your nuclear fusion has started in the core of your star. And at this point, the star effectively switches on like a light bulb, And suddenly, for the first time, there's light in the universe, and the universe, ping, 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 suddenly lights up, and that light then leaves the star at the speed of light and is still going. And so that's where the very first stars came from. And these stars were very, very big because they've got a lot of fuel. They've got a lot of stuff that they can pull in under gravity, and so they're massive. It gives them all the energy they need to run through the life cycle of a star, which is an interesting thing. And so what's going to happen inside your star is you've got a big ball of hydrogen, a big ball of very hot hydrogen, and in the very middle it's hot enough and dense enough for that nuclear fusion reaction to be starting. And that nuclear fusion reaction, remember, is turning two hydrogen atoms into a helium atom, generating a whole new element, which is heavier than hydrogen, and so it sinks to the very centre of the star. And so in the core of your star, you're generating a new core of helium. And that helium core now gets bigger and bigger and bigger as this process runs on, collects, all sinks to the middle. And you've now got an increasing sized core of very, very hot, very, very dense helium. And eventually that helium core gets big enough and hot enough for the atomic nuclei to get squeezed together close enough, and you start to get nuclear fusion happening again between helium atoms. And the helium atoms fuse together to make, sorry, I've forgotten what it makes. Your helium fuses together to make carbon. And so carbon is another element in the periodic table. It's basically just a collection of more protons and neutrons in that atomic nuclei. And so we make carbon. So now we've got a star made of hydrogen with a shell, effectively, of helium, which is undergoing nuclear fusion, making carbon. So you've got your hydrogen fusing to make helium, your helium is fusing to make carbon, and you're getting a carbon core in the very centre of your star. And then, given enough time, that carbon, the carbon's heavier than everything else in the star, so it sinks to the centre of the star. And you get a football of carbon in the middle of the star, which gets bigger and bigger and bigger until that is hot enough and big enough and dense enough that the atomic nuclei get squeezed together hard enough, and you get nuclear fusion happening in the carbon atoms, and they fuse together to make oxygen. So now you get an oxygen core in the centre of your star, and this process carries on going. And so I've got a picture. Sorry, very high tech. I'm just going to move the camera. Uh-huh. And this is what you end up with. You have to have a very, very big star for it to be able to get through all this process. So our own sun doesn't get this far. Our own sun is too small, and so our own sun is a hydrogen star fusing hydrogen to make helium, and it's got a helium core, and that's it. It isn't big enough to go any further. But the very first stars that were huge, you ended up with a hydrogen shell. The majority of the star is still made of hydrogen. And within that, you've got a helium shell, which is fusing to make carbon, and then you've got a carbon shell, which is fusing to make oxygen, an oxygen shell, which is fusing to make neon, a neon shell that's fusing to make magnesium, magnesium shell that's fusing to make silicon, and in the very centre you have an iron core. And that is what happens if you've got a big enough star with enough fuel and enough time. You get this shell structure with hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, and iron at the very centre. And so we started with nothing but hydrogen, and if you've got enough of it and enough time, you end up with hydrogen plus 1, 2, 3, 4, 5, 6, 7 more elements. So we've now got 8 elements that exist in the whole universe, which is a hell of a lot more than we started with, but still not very many. So the periodic table, which is a map effectively of every element in the universe, contains a lot more than 8 elements. But we haven't got them yet. So we're still in the early universe, and we've got stars. Well, in the early universe, when you've got these first stars kicking around, all there is hydrogen gas and a smattering of helium spread out across the universe, clumped together into stars, and those other 7 elements are contained, locked up within these small point sources where they're stuck because of gravity. And that's all the elements that there are, and that's the way it was for quite a long time. And what's actually happening is your hydrogen releases a huge amount of energy when it fuses to make helium. Your helium then produces a lot of energy, but a lot less when it fuses to make carbon. Your carbon produces a lot of energy, but a lot less still to make oxygen, and so on. And so the energy that you get that gets released by the nuclear fusion reactions gets less and less and less and less and less as you approach iron. And when you get to iron, this fusion process stops. Iron is the end of the road for generating elements by nuclear fusion. And what happens in a big enough star is you still end up with an iron core, in that iron's the heaviest element in the star, so again it sinks to the middle, gets bigger and bigger and bigger and bigger and bigger and hotter and denser, and you might expect it to collapse and fuse to make another element, but it can't do it. And we'll come back to why later on, if I remember. So eventually your iron core gets so big that it will collapse, and those atomic nuclei get squeezed past the electron shells and slam into each other. But instead of fusing and making another element, this iron core collapses to make one big, massive ball of neutrons. So it's just a ball of neutrons, which is tiny. Remember, the center of an atom is tiny in comparison to the size of the atom. The center of a solar system, the sun, is tiny in comparison to the solar system. The center of a galaxy is tiny in comparison to the galaxy. Everything is almost all empty space, and that carries on going. The smaller and smaller, smaller down you go. So your neutrons, your ball of neutrons, is tiny in comparison to that ball of compressing iron atoms that you started with. It suddenly goes down to a ball of neutrons, and it doesn't fuse to make more, to make another element. And so instead of collapsing and then going and loads of energy coming out, and that's sort of supporting the pressure on the inside of the star, this ball of iron collapses and stays small. And so now you've got a void in the middle of your star, right in the core. Suddenly there's nothing there. And so the rest of the star momentarily crunches in, hits that solid ball of neutrons in the middle, and the shock wave just blows it to bits, and you get the most awesome explosion you can ever possibly conceive. If you think a nuclear explosion is big, this is on another level. The only bigger explosion that there's ever been in the history of everything is the Big Bang. The Big Bang was just a whole another stupid, ridiculous kettle of fish. But this is called a supernova explosion, and it's an exploding star, and it is nuts how big and how bright these explosions are. And there's a good graphic. Oh, there we go. So bear in mind, this is a star. So in the middle, where's the camera? In the middle there is a star which is about to explode. And then it explodes into a huge explosion. And this explosion throws all the matter, all the stuff that's inside that star, gets thrown out and spreads out, leaving behind that solid ball of neutrons in the middle of the star, which ends up staying there. It's called a neutron star, which is just ridiculously dense and tiny. But basically, the star explodes and spreads all of its elements that it's been manufacturing, spreads them out across its local part of the universe. And that is a long way. This is a big enough explosion that if our nearest other star, that's not the sun, if the nearest other star did this, it would destroy we would be within that blast radius. It is stupidly huge. And so this cloud of debris from your exploding star spreads out across the local part of the universe and cools down as it does, and eventually settles down and this happens kind of all over the place, if you like. Just sort of all over the universe, there's all over the galaxy, there's just sort of stars growing and then bursting, in these huge supernova explosions, they're called. And so now you've now got new stuff which collects, where's my picture? Collects into what's called a nebula. And a nebula this is one of my favourite pictures ever. This is taken by the Hubble Space Telescope. And this is a nebula, which is a cloud of dust and debris from exploding stars that has coalesced under gravity in order to form these huge, dense clouds of all sorts of elements. And then new stars then form within these clouds. And so these are known as stellar nurseries, and they are ridiculously big structures. You can see stars forming within it. It's got little bright bits. If you look up the pillars of creation, this photo is called. It's I can't remember what the actual. It's called the Eagle Nebula. That's this proper name, and it is littered with stars starting to form within that nebula. So, when our supernova explosion happens, that's going to blast all those new elements. And remember, we've got hydrogen 3 to iron, so we've got 8 elements getting blasted out into space. But during this process, the temperatures and the pressures within that exploding star are so great that all the other elements of the periodic table, every other element in the periodic table, gets manufactured via, during the supernova explosion. In the actual moment, in that huge shockwave, there's enough energy there to fuse together what's there in order to manufacture everything else. And so, after you've had a first generation star, which was very simple, so it starts as nothing but hydrogen, gets more complicated until it's got those 8 elements in it. That then explodes in a huge supernova explosion, and that generates all the other elements in the universe. And so your nebula that forms out of that has now got all the other complicated elements in it, so things like gold and silver and plutonium and uranium and all of the other stuff that we need, that we have, all came from supernova explosions from those first generation stars. You then get a nebula forming, which is now quite a complex soup of all of the elements in the universe. And so now a second generation star forms, and you get basically the same process again, but this will now have some contaminants in it, if you like. It's got a second generation star is going to have a little bit of gold and a little bit of uranium in the middle of it, not enough to form nuclear fusion reactions, but so the same normal nuclear fusion reactions happen, but you've got these other elements in there as well. And then eventually that's going to supernova, coalesce into a nebula, and a third generation star forms, and that's where we're at now. So our sun, they reckon, is a third generation star, and so it's fully complex. Our star system, which coalesced out of this nebula, and the planets that formed at the same time as the sun, have got all of the elements that you get in the universe as far as we're aware. Which is great, because it means that the Earth has got all the stuff in it that we might need. And it's got all the stuff in it that you needed to, all the complex elements in it that you need for life to evolve and all of that. Life couldn't possibly have evolved on a planet that had formed from in a simpler universe and a simpler time of the universe when there wasn't all the elements available for it to happen. So we're on a third generation star, and our star is too small for any of that supernova rubbish to happen. There isn't enough fuel there. It doesn't get big enough and hot enough. So our star is a hydrogen star with helium collecting in the middle, and there's a load of other elements in there, but nothing complex happens in terms of nuclear fusion because it's not big enough and not dense enough. So the sun's got everything in it. There's even water, found out the other day, even water in the sun, they reckon. Not a lot. Yeah. So where are we at? I got lost again. Oh yeah. So this is all just gravity. Gravity has done all of this all by itself. This is one of the best things about science, is you start with nothing but a diffuse cloud of gas and gravity, and you end up with third generation stars and the Earth. It's just awesome. You don't need any kind of plan. You don't need any kind of higher power conducting it all like an orchestra. It just happens spontaneously. All you need is stuff, time, and gravity, and you get this. And it's just a force field. Gravity is just a force field which acts on a universal level, and it gets less and less and less the further away you get from stuff. But in the absence of anything else, in a total vacuum with nothing else at play, gravity will win out over everything else. Well, there isn't anything else. There's just gravity. Gravity is the only force that acts at distance. But it's just a force field. Then when you get smaller, when you get down into the structures of atoms and compounds, you've got your, before you get there really, you've got your electromagnetism. So you've got electromagnetic force, but magnetic fields don't have any influence outside of their magnetic field lines. And so if your magnet is huge, like the core of the Earth, then your magnetic field is the size of it sort of extends outside of the atmosphere of the Earth, but it's relatively small. There's no magnetic influence of the Earth's magnetic field on the Moon, for example. It's too far away. If I have a magnet on one side of the room, it has absolutely no influence magnetically on a magnet on the other side of the room. They're too far away. Magnetism works effectively on a relatively small scale, and electromagnetism is a whole other subject, but it's a relatively localized effect. Not as localized as the other two. Remember, we've got the weak nuclear force, which holds atoms together. And that's relatively weak. Say weak, I mean it's holding atoms together into molecules, so it's relatively strong in terms of comparison to things like gravity. No, gravity is not very strong at all. You've got the whole of the planet Earth pulling you down onto it. But you can still jump off of it momentarily, at least. You're not flattened to the surface of the Earth because it's not that strong. Whereas the weak nuclear force is pretty significantly strong, but nothing in comparison to the strong nuclear force, which is the force that holds your atomic nuclei together. It bonds those protons and those neutrons together, which is absurdly strong. But each of these forces, all they are is force fields. So gravity is just a force field holding atoms in their big structures, making galaxies and solar systems and planets. And when things get close enough to be able to, for those atoms to be able to react chemically with each other, you get the weak nuclear force doing its thing, and that's just a force field. Magnetism, obviously just a force field. It feels like a force field. But the weak nuclear force is just a force field holding things together. And your strong nuclear force is just a force field holding things together. And at each stage, what you realise is that there isn't really anything there. All you've actually got is the force field. which is an odd concept, really. So your atoms are almost entirely a force field. You've got a little solid lump at the middle, you've got your nucleus at the middle, and this force field of electrons around the outside, but it's almost entirely empty space, and the electrons kind of aren't really very much there. It's almost entirely empty space, almost like a solar system. You then look at an atomic nucleus, and it's a bunch of neutrons stuck together, but each of those neutrons, and what's a neutron? It's not a solid lump. A neutron, if you smash, this is what they're doing at the Large Hadron Collider, is they whiz them around in circles ridiculously fast, almost the speed of light, but not, because you can't, really fast, and smash them together so they break apart, and they've got these amazing detectors that then measure what comes out when you smash things apart. And what you get is a few very, very, very tiny little particles come out of neutrons. And again, it's the same sort of thing. A neutron or a proton is just a force field with a few very dense little particles whizzing around in it, called quarks. And at the moment, they believe that quarks are fundamental particles, and they actually are there, and they are solid. But it wouldn't surprise me at all if in the future they realise that they're the same sort of thing, and it's just a force field, and there's something smaller in the middle whizzing around. And so, certainly at the moment, what we know is that quarks are the most solid things that we're aware of, but they're ever so small. And they are the solid bits that make up the big empty sphere of nothingness, which is a proton, that makes the big empty sphere of nothingness, which is an atom, which makes the big empty sphere of nothingness, which is the solar system, which makes the big empty sphere of nothingness, the galaxy. There is nothing there the whole way until you get down to a quark. And the only thing that is there are these force fields. Which brings us on to the important bit, really, which is wondering, what is nuclear power, really? We'll come back to that in a second. Because there's another kind of nuclear power. We talked about nuclear fusion so far. The other kind of nuclear power is nuclear fission. And so on our periodic table, we started with hydrogen, we went up through those elements that we managed to create, and we stopped at iron, because you can't go any further than iron. Remember, there's less and less and less energy being created by those nuclear fusion reactions until eventually you create iron. And then anything else this way is all made in the supernova explosion, in that ridiculously dense pressure wave. And so nuclear fission is the opposite process. It's breaking elements down into smaller elements. And so you can only do this with big elements, really. So that's why they tend to do it with things like uranium, which is a huge, it's got 235 protons and neutrons, I think, in its atomic nucleus, which is a lot more than one in a hydrogen. So absolutely enormous atom structurally, and you can break that into smaller things. When you break into smaller things, you get a lot of energy being released. And so radioactivity is a bit of an odd thing. Again, that's a whole subject in itself, really. But basically, there are certain elements which are not stable. And so elements like iron are perfectly stable. You take an atom of iron, you can leave it there and it will just stay an atom of iron forever. If you take an atom of uranium, it's got a tendency to want to just fire off a neutron out of its atomic nucleus, and that randomly a neutron will just jump off of a uranium atom, jump off of that atomic nucleus and just ping off, leaving a slightly lighter nucleus behind, which is a different element. So uranium will all by itself. Uranium is an element which exists naturally on the Earth. You can dig it up. You can, if you go to the right, if you go to Australia, you can dig a hole and dig up uranium if you're in the right place. And this stuff will just, it's a radioactive, and what that means is that it will randomly ping off a uranium atom. Just 2 secs. I'm finished with that. You can have that. We're sharing laptops. It will randomly ping off a neutron and turn into a different element, turn into a lighter element, which is mad. And so this happens randomly. If you take a lump of, if you dig up a pile of uranium in its uranium ore, which is basically mixed with rock, it will be randomly pinging off occasionally neutrons out of it. And these don't do you very much good if they hit you, because they're going very fast and they can damage your DNA, which is why it's not good to be near radioactive stuff. But what's happening is your heavy uranium is turning itself entirely by itself, entirely spontaneously, turning itself into a lighter element. If that proton that pings off of your uranium atom, if that happens to hit the very, very small atomic nucleus of another uranium atom, which remember is very unlikely because they're very, very small, if your proton happens to actually collide with another uranium atom, then it smashes that uranium nucleus apart and forms a load of different lighter elements, some of which are radioactive in their own right and some of which aren't. So that's unlikely to happen because your uranium nucleuses are so small in comparison to the atoms and in comparison to the rocks around them. It's be like shooting a bullet off into space and worrying that it might accidentally hit Jupiter. It's just not going to happen unless you've got enough uranium atoms in a small space, and then it's relatively likely to happen. And this is what happens inside a nuclear reactor. What we do is we dig up uranium, which comes as an ore, which comes as basically uranium mixed with rock, so relatively diffuse. We then collect it all up until you've got a lump of it, and all you need is a big enough lump of uranium, and it will start this process of, when they're close enough together, the likelihood is, the probability is that a natural pinging off neutron will collide with an atomic nucleus of another uranium atom, smash it apart, and then in the process of doing that, something like 2 or 3 random neutrons end up pinging off. So now you've made more random wayward neutrons, which collide with other atomic nucleuses, smash them apart, and now you've got more, and all of a sudden you've got this chain reaction, it's called. It's a runaway reaction, where suddenly there's enough neutrons flying around for it to happen more and more and more and more and more and more and more. And every time this happens, it releases heat. So all you need to do, so we said earlier that nuclear fusion was incredibly difficult to make it happen. Nuclear fission is incredibly easy to make it happen. All you need to do is make a big enough pile of uranium and it will start to get hot. And there's what's called a critical mass, which is a certain mass of uranium in a small enough space, and it will start to get hot, like really, really hot. And we use that to generate heat, to boil steam, to turn turbines, to make electricity. But all you need to make nuclear fission happen is to get enough uranium together in a small space, and it gets really, really, really hot. If you spread it out again, then it cools down. And the complexities of a nuclear power station are a little bit more complex than that, but that's the idea. So we got 2 ways of releasing energy from nuclear reactions. You've got nuclear fusion, which is joining stuff together, and you've got nuclear fission, which is smashing stuff apart. Nuclear fusion leaves you with nothing but the next heavier element, and so in reality the majority of this is hydrogen getting fused into helium, which is, you can breathe it, it's totally safe, there's nothing wrong with it, it's nice stuff. But it's very difficult to make it do it, because you've got to have the temperatures and the pressures of the centre of the sun, which is very, very hard to generate on Earth, especially without melting whatever it is you're doing with it. So containing that energy is the difficult thing. Nuclear fission, which is breaking stuff, is really easy, but what you end up when you smash a uranium atom apart, you don't get just a few nice little things. You get a collection of random smaller elements, some of which are really, really nasty. And it's totally possible to break apart smaller elements than that, but it's much easier to do it with big heavy ones, and so that's why they choose heavy elements like uranium rather than doing it with something that's a little bit lighter. It's because it's naturally radioactive, and so all you've got to do is put it in a pile and it heats up. And again, the problem there becomes controlling that reaction, managing those random neutrons that fizz around. And you actually do that with carbon. If you stick carbon, if you make rods of carbon and you stick them into this pile, they absorb the neutrons, so it stops the reaction from happening. But it basically is a very easy kind of, in comparison to fusion, a very easy way of making a lot of energy. Sorry, not making energy, of releasing a lot of tied up energy, which is ultimately energy from the Big Bang, remember, that's made its way into these bonds. A relatively easy way of achieving releasing that energy into heat and changing the structure of things. But it produces some really, really nasty radioactive material, which is then a legacy for literally the next 100,000 years, which we can't really plan for because we don't even know if the world's still going to be here in 100 years. We need society to manage nuclear waste for the next 100,000 years, and it's probably going to fail at that. So we're leaving behind a radioactive legacy of stuff that doesn't tend to exist in nature unless it's been produced inside a nuclear fission machine. And like we said before, is that as bad as releasing a load of carbon dioxide into the atmosphere by burning all the coal and changing the composition of the atmosphere and screwing themselves over that way? And this is the problem. It's like, what's worse? And the answer is, it's all bad. Anyway, whatever. Humans are the problem. There's too many people. So we're nearly finished, but there's an important point, which is the point, really, which we'll try and get to in a second. You got energy by fusing. You released energy by fusing together hydrogen to helium, helium into whatever. And the closer you got to iron, the less and less energy you get out of that fusion reaction. You get energy by smashing open uranium, and you get energy by smashing open lighter elements as well, but it's harder to do. And it becomes harder to do, and you get less and less energy out until you get to which element do you think? Iron. So iron is like a crossroads in the periodic table. Below iron, you get energy out by fusing elements into heavier things. Above iron, you get energy out by breaking things into smaller and smaller bits. And this is why the fusion reactions in the middle of a star stop at iron, is because above that, you don't get energy out by fusing stuff. It takes energy to do it. And so that's why it stops at iron, and you can end up with these supernova explosions, which then spread stuff around the universe. So thank goodness it is like that. Otherwise, all the heavy elements in the universe would still be stuck in stars. And it all seems a bit weird, and it all seems a little bit odd until. Sorry, Nikki's stolen my laptop, so I've just got to find very, very quickly. No, it's all right. I'll find it here. Just sing some lift music or something. There we go. It all seems a bit weird. That's as good as it's going to get. Until you think about what energy actually is. And this is kind of the point of the last 45 minutes. And you probably heard of Einstein, a very clever man. He came up with the answer really of what energy actually is, and he's got his famous equation, which is that backwards? Is that filming it inside out? Oh, God, computers are weird, aren't they? Anyway, you got look at it in a mirror or something. So his famous equation says in mirror form, E equals mc squared, which is all very complicated and difficult to get your head around. And oh, isn't it difficult? Isn't it difficult? Isn't it? No, it's not. It's really, really not difficult. It's really simple. Couldn't be more simple, actually. All this says, I really don't understand why it's doing that. All this says is energy equals mass times c squared. And c is the speed of light. C is a very, very big number. Speed of light is very, very fast. C squared is just an absurdly big number. So c squared is a constant. C squared is just a massive, massive number. And so what this actually says is energy equals mass times a massive number. And so what that says is energy equals mass. And that is the most important point, really. Energy is mass, is energy, is mass. They are equivalent, they're the same thing. Energy is mass, which, again, seems a bit weird until you remember that what is mass? Mass is just a force field with a force field in it, with a force field in it, with a force field in it. It's just energy. So energy and mass are equivalent. They're the same thing. In a different form. And so when you've got nuclear reactions happening, if you're fusing two atomic nuclei together to make a heavier one, and in the process you're releasing a load of energy, what do you think happens to the mass that you've got left? If you started with something that weighed 2 whatevers, we'll just call it 2, and another thing that weighed 2, and you fuse them together, you might expect something that weighs 4. But it doesn't. It weighs 3 because you've released a load of that energy. And so what you're doing in this is the point. What you're doing in nuclear reactions is you are turning mass into energy. You're destroying some mass and turning it directly into energy. So every time you fuse things together, your heavier element that you're manufacturing is slightly lighter than the sum of its parts by, I believe, 0.07%, so nearly a whole percent lighter. And that mass is turned directly into energy because it's effectively taking the energy from the force fields and releasing it as heat. When you've got nuclear fission, you're breaking a heavy element into two smaller things or into a bunch of smaller things, and the mass that's left, if you smash open a uranium nucleus, you release a load of heat. If you collected up the smaller elements that you created in this fission process and then weighed them, they would be lighter than the thing that you started with because you've turned some mass directly into energy. E equals mc squared. It just says energy equals mass times a number. Energy equals mass. And so that's what nuclear fusion is. That's what nuclear fission is. That's what nuclear power is, either way, is you are turning mass directly into energy. You're not creating energy because that mass is made of energy, which came from the Big Bang. You're just releasing it converting it, turning it into heat instead of the complex system of force fields that is matter. The end. Bye.